Hello, in this question I'm going to go through what is essentially a difficult projectiles question with a rotated frame of reference. Now, this is taken from a University of Cambridge engineering entrance exam paper from 2016. So before we get into what they're asking us, let's have a look at the scenario they've given us. So we've got a cyclist coming down this slope. So he's coming down a slope section, then he's on a flat bit, then a slope section again. Both of the slopes are at an angle of theta to the horizontal. He starts at rest at A. In riding down the slope, transfers an amount of energy E from his muscles to provide kinetic energy, descends through a vertical distance H, leaves the track at B, jumps over this obstacle, lands at C, a distance L down the slope. We can assume that the rider bicycle system can be modelled as a point mass of mass capital M, and there's no friction, no air resistance, and the gravitational field strength is G. Right, so that's our setup. Now, there's four parts of this question. I've split them out because I can't fit them all on the screen. So here are the answers to the first part, which is essentially they want us to say, what is VA? So when we got to B, and this cyclist is moving with velocity v at B, the components of that are VA parallel to the slope and VN perpendicular to the slope. So we want the component of the velocity parallel to the slope when the cyclist reaches point B. Okay, so we can do a conservation of energy approach on this. So when we start off at point A, we've got the cyclist is at rest and is adding then the change in potential energy and this amount E in order to get the final kinetic energy. So we're going to have an mgh plus E is going to be equal to our half mv squared. That's what we've got. So we just need to solve this for V and then get the component parallel to the slope. So multiply by 2 over m, it's going to give us 2gh plus 2e over m is equal to v squared. I'll just get the v on the other side. So v is going to be the square root of all of that, 2gh plus 2e over m. And then we can see that the component parallel to the slope is v cos theta. So we're taking that and we're multiplying by cos theta. So in terms of the potential answers, before I put that in, because we might have to reformat it a little bit, we want the ones that have got multiplied by cos theta. So not that one, not that one, not that one. It must be one of the other two. Both of them have got a factor of 2. So it's not both terms have got a factor of 2. So it's not the top one. So it is the bottom one. So let's just write it in that format. That VA is v cos theta, which is equal to, well, you can see it's this, they've just shuffled it around a little bit. So the square root, we've got the cos theta at the end, and then we've got this 2e over m plus gh. So that's not too bad a start there to get our first bit. Right, let's try the second part. So in the second part, they want us to work out the time to go from B to C. So that's what we're looking at now. So this is where it turns into a projectiles question, because we've got now, if we look in the component perpendicular to the slope, this is a standard projectiles question of what is the time of flight, but we don't have the standard gravitational acceleration because everything's been rotated. But we can do SUVAT because we got a constant acceleration. So we're wanting to have a zero displacement in the perpendicular direction. So this is in the n direction is what we're looking at here. In the n direction, we want to have a displacement of 0, because that means we've got back to the level of the slope. Our initial velocity is the v that we worked out in the last part of the question, and we can see everything here is in terms of v's, not va, so we can stick with that. We've got v, whereas before it was v cos theta, we want v sine theta on this. That's our component of the velocity perpendicular to the slope at point B. V we don't really care about. The acceleration, right, so we need to think about what's going on here. So we've got an acceleration which is going straight down like this. This is our G. We've got a component which is perpendicular to the slope. That's our N direction. So let's put all our angles in. So if that's our V, we know that that's theta, which means that must be theta, which means we've got a cos theta minus cos theta of this for the acceleration. So we're going to have minus G cos theta. So it's still minus because the velocity we're measuring upwards. The velocity we're taking positive to be that way. When we take the cos theta, the component of the acceleration is going in the opposite direction, so we want a minus there. And then we want to work out what t is. So we're doing suvat on this. With these more complicated cases, it's another one where suvat can be useful rather than trying to talk all of your way through this in terms of, you know, aggregations of quantities and all this sort of thing, accumulations of quantities. That's just going to be just insane trying to do it where we've got acceleration in both directions. So let's stick with this and doing suvat because it's safe on a complicated question. So we're going to use s equals ut plus a half at squared. And we know we can divide by one of the t's because we don't want the t equals 0 solution. We want the other solution when it's come back down over at c. So we're going to be saying that s, which is 0, is going to be equal to u v sine theta minus a half of the acceleration. So what I put in the minus from the acceleration, minus a half of the acceleration, so a half g cos theta, multiplied by t, because I've divided through by the t to get rid of the 0 solution. Right, so now we just got to solve this, and that will give us what t is. So we're going to have that t is going to be equal to 2v over g multiplied by tan theta, just doing a quick rearrange on that, which is giving us answer B. So yeah, not too bad. It was, I think the main awkward bit was getting this acceleration in the right place, getting the right component of that gravitational field strength. So that's the second part. Right, part 3. We're now wanting to get what L is. So what is the distance from B to C? Okay, so we've got the travel time. So the travel time that we had before in the last part of the question, I'll just write that out again. It was 2v over g multiplied by tan theta. So that is our time of flight. So now we can do suvat parallel to the slope. So you've got to remember with this that although we're doing parallel to the ground, we've now got an acceleration in this. And it's going to be a positive acceleration with the sine component. If we go through the same process that we had before, then this acceleration here, we've got a sine theta, the cos 90 minus theta, and it's going in the same direction as the component of the velocity. So it's going to be a positive acceleration. Our initial velocity was, that was our v cos theta. We need to find out what s is. Again, we don't care about v, and we know what t is. I've written it at the top. So s is going to be u times t, so that is 2v squared over g sine theta. and then we're going to add on the half a times t squared. So we've got a lot happening here. So a half times g sine theta times, then we've got to do t squared. So 4v squared over g squared tan squared theta. So there's a lot of terms here, but we're hoping we're going to get a lot of things cancelling out. So we can cancel that g with one of the g's down there. We can cancel that half with that to bring us a 2. So we can already see that both of these terms have got 2v squared sine theta over g. So let's factorize that out. 2v squared sine theta over g. So the first term, that is the whole of the first term, so we've got a 1. What's left here? 2v squared sine theta over g. All that's left is a tan squared theta. Tan squared theta. So, right, that doesn't quite look like any of these at the moment, but off of our what do you call it? Your trig identities. That's the term I'm trying to think of. Trig identities. So 1 plus tan squared we know is sec squared. So just to run through that in case you've forgotten, sine squared plus cos squared equals 1. Divide everything by cos squared, so we get tan squared plus 1 is 1 over cos squared, which is sec squared theta. So doing all of this, we got a sec squared in this for 1 plus tan squared, so that is going to be 2v squared sine theta over g cos squared theta, which hopefully is one of these, which is C. So you got your trig identity part of it filling in the gap on that one. All right, so moving along, I think that's probably the most difficult part we've had so far. And the final part of the question is to work out the maximum height. So they want to know how big an obstacle can we stick in this this gap from B to C, and where should we place it so that the rider can jump over the largest obstacle possible. So where are we placing this obstacle to make it as big as possible? Right. Now, in this one, we're really looking for, as I say, the maximum height. What's the maximum distance away from the slope that the rider is going to get to? So we're doing another suvat on this. Because if we can get the time that it reaches that maximum height, then we can work out how far the cyclist would have gone along the slope. So we want to work out, well, actually, we don't care about what the height is. We care about, well, we know this initial velocity. It was our v sine theta. We want to have the component of the velocity perpendicular to the slope being 0, as we normally do in projectiles. That tells us the maximum height. We know that the acceleration is minus g cos theta for all the reasons that we had before, and we want to work out what the time is. So we can whack that into v equals u plus at, which means that, yeah, if we put that, just write that out, v equals u plus at, that will give us what the time is. Velocity is 0, so this u is going to have to be a times t. So u over a is t, so it gives us a time of v over g tan theta. That is our, the time that we've reached that maximum point. So now we need to work out how far along the slope have we gone, looking parallel to the slope. So we want to know what S is. That's what we're trying to work out. We know that this is v cos theta because we've done that many times before. We don't care about v. A we know is g sine theta, and t we've now got is that. So now we need to work out what s is going to be. Well, this is going to have a lot of components in it, and I'm running out of screen. So let's just section off this little bit. So we're doing an s equals ut plus a half at squared. So s is going to be u times t. So that's v squared over g. Tan theta times cos theta is sine theta. Then we've got to add on a half of a times t squared. I'll put this on a second line for this. So a half of a, which is g sine theta, multiplied by t squared. So that's v squared over g squared tan squared theta. Right, now if we add all of that up, hopefully again we're going to get some things that simplify. Right, we've got v, that g is going to cancel with one of those. So again we've got v squared sine theta over g in both of these. So that's v squared sine theta over g. We can factorize. That's the whole of the first term, so we got a 1. So this is already looking like it's going to be d. So let's just check we got the remaining bits. And we do. We got a half tan squared theta. And lo and behold, we've got that bit. So in terms of the actual methods we're using, this is just standard SUVAT. The thing that makes it more complicated is we've got a component of the acceleration due to gravity both parallel and perpendicular to the slope, which is not what we're used to in projectile motion, where we're used to just having acceleration in one direction and then no acceleration in the other direction. Here we've got acceleration in both directions, which is what's testing our ability to apply SUVAT effectively and efficiently. So yeah, it's a great way to see if you really can do SUVAT well and do projectiles well by rotating your axes. And you could do this on any projectile question. It'd be interesting just to take a standard projectile A-level maths question and say, you know what, I'm going to rotate my axes by 30 degrees or something like that, and just see if I can get exactly the same answer by doing that transformation of frame of reference. Yeah, great practice for your mechanics and your algebra and everything else. So yes, a lovely question, this one.